Welcome back to some more nonsense about electrons, protons, orbitals. This one is Slater determinants. But rather than jump right into the Slater determinant mechanics, let's look at some spin orbitals. Here's helium. We're just going to look at atoms rather than molecules. Here's helium, and it's got a nucleus of +2, and so to balance it out, if it's a neutral atom, we need 2 electrons. And these 2 electrons can both occupy, like we talked about in the last Pauli exclusion principle, can both occupy the 1s orbital, providing they have opposite spin, because the spin creates a unique state. So here's electron 1, 1s1, alpha 1, where alpha equals up, and on this one, beta equals down. So this is the 1s for electron 1, and the spin for electron 1. This is the 1s for electron 2, and the spin for electron 2. Now on the next screen, we're going to look at the Slater determinant of this to figure out whether it satisfies the antisymmetric requirement. And we'll also cover lithium, where it's got 3 electrons. First 2 electrons occupy the 1s orbital, and this third electron has to go up to the next energy level, the 2s orbital. So there's the third electron notation. Now we're not going to go all the way to this right now, but just to give you an idea, here's carbon, and I'm showing the 1s and the 2s orbitals, which get filled by 4 electrons, and then the 5th and the 6th electron go up to p orbitals. And you can see the px and the py orbitals are filled, and also their spins. Now this just kind of gets your head ready to look at the Slater determinants for helium and lithium. Here's helium. This stuff inside these big 2 lines is considered a determinant, and this is matrix algebra stuff. But let me just show it to you in this way, show you how we do the evaluation of this determinant. We take the left corner, multiply by the lower right corner, and then we subtract the right corner times the lower left corner. And that's what I've done right here. Here's electron 1s, here's electron 2s, and here's an alpha and a beta, and all these are the different possibilities that could occur. Now let's look at this. If we swap 2 electrons, then the difference will switch around. Let's see if that's true. The only difference between these is the alpha and the beta. If we switch the 1s and 2s, the alpha and beta switch around, and we reverse the difference, which causes a sign change. So that's really what we want to see is, if we see that sign change and this doesn't equal 0, in other words, if these were exactly the same, then we'd be subtracting the same thing from itself, and this would be 0, then that would say that that possibility can't occur. So this one does. We'll worry about this normalization factor later, but essentially it's 1 over the square root of the number of orbitals factorial. So that's 1 times 2 is 2 factorial, gives us 1 over the square root of 2. Now if you're ready, or even if you're not, let's go on to lithium. Okay, I've punched all this stuff out. Here's a 1s alpha, 1s beta, and a 2s alpha. Well, we can look at the second electron could go through these same states, and the third electron could go through these same states. Now that doesn't say that electron 1 has to be on the 2s orbital, but it could be on the 2s orbital. So these are all the different permutations, if you want to call it, of these different items. Now, to keep our notation a little bit simpler, let me say x sub A equals 1s alpha, x sub B equals 1s beta, and x sub C equals 2s alpha. Those are the three orbitals, really, that we're talking about. Each one is unique because even though these are both 1s, they have a different alpha value. So I've filled this thing out with the 1 in parentheses. For the first electron, here's the second electron, here's the third electron, and here's the way I have to calculate this. I'm going to take x sub A and multiply it times the quantity. And if you look at these four elements here, you take A and just wipe out those. That leaves this little corner section that A can operate on, or A can be multiplied by. And here's the difference function between those two. And if we look at this difference function, if we swap 2 and 3, then we've inverted the difference. And so I put a little red check mark beside that, just like the red check mark up here. Shows that that's a valid combination. Now if we take x sub B, then we wipe out this row and column and just take these four elements. So you'll see I've got the x sub A, xa of the second electron, the x sub C of the... So working this one out, I take this one times this right corner and this one times the left corner. And that's what I've got here. And we can follow the same thing with x sub C, and we take these four elements and form this difference. If we check out each one of these and put a little check mark on it, all of these satisfy the antisymmetry requirement that you swap two electrons and the sign changes. If I multiply these out, I end up getting 6 terms. And those 6 terms, if we look at each of these groups of differences, now notice it's got this minus sign out here because of the way that this minus and plus thing worked. And I hope you can follow along that this is these 3 pairs of terms actually describe the swapping of 2 and 3. Well, what happens if we swap electrons 1 and 3? Well, you look here and that doesn't work out right. That isn't going to give us the difference that we're looking for. So these paired up terms only work for 2 and 3 swaps. Well, on the next page, I'm going to show that we can come up with 3 groups of terms that satisfy 1 and 3 swap, and 3 groups of terms that satisfy a 1 and 2 swap. Just to show that all these different combinations can be verified as satisfying the antisymmetric rule. Okay, here we are. From the last page, this was swap 2 and 3, and notice that the 1 remains the same, but 2 and 3 are swapped. Now, if we take these same terms, but pair them up differently, then for swap 1 and 2, you notice that the electron 3 doesn't change, but the 1 and 2 get reversed. Same terms. And finally, the 1 and 3, you'll notice electron 2 does not change between the terms, but the 1 and 3 are reversed, so they satisfy the antisymmetry. You can freeze this and look at it and verify it some more, or you can just take it on faith that all of these conditions are handled with these determinant generated terms.